Hey everyone, welcome to this second video of the series. In this video, I'm going to be going through a couple of basic modeling exercises inside of Rhino. So we're going to start by just going ahead and opening either a blank Rhino file and you can follow along, or if you have access to the project files, go ahead and open up the day one exercise files 1 base file to get you started. So this is mainly just going to contain a template for the modeling exercise that we'll be going through. There's no kind of need to follow along through this template. However, it's just to keep it organized as we step through each of the steps. And if you need, yours are going to be populated already, so you can turn on each individual layer for each step, which should have labels there to just describe whatever that operation was to jog your memory in coordination with the video. So as I'm making this right now, I don't have any of those layers in this file, but you'll have access to the finished file to review and look at as you go through. So first off, what we're going to do is be kind of combining a couple of the geometry types as well as geometry operations that I went through in the first video. And the first thing or two things that we're going to be doing are making two different types of platonic solids from scratch. The first is going to be a tetrahedron, which is a triangular pyramid, or a kind of four-faced, but you might think of it as three sides, three-sided pyramid, where the fourth face is the bottom. So one of the special things about a tetrahedron, or also the second platonic solid that we'll be modeling from scratch, which is an octahedron, is that each of the edges in a regular octahedron or tetrahedron are equidistant, meaning that if we use a base unit of 10 for each of the edge lengths, then every edge in the system will be the same. And this is a crucial aspect of something like what we'll get into later on in scripting, which is recursive aggregation, because we'll already know from the start that each of the faces are going to be able to pair up with one another to kind of stack and fill space or branch. Not that all tetrahedrons or octahedrons can evenly fill space or fully continuously fill space. We'll get into that again a little bit later on. But it is a good base starting point to kind of limit some of the parameters. So mainly we'll be starting with modeling those two platonic solids, and then from there we'll be combining them, and this is going to be a little bit more of an intuitive process, starting to look not at the kind of scripted version of aggregating them, but just some transformation and translation options inside of Rhino to kind of build up a design intuitive sense about these objects and how they might stack or assemble together. And then we'll do some post-processing of these to start to kind of reshape, and then finally we'll close it out by thinking of this as a model. So if we were to digitally fabricate this model by unwrapping it and all of its faces, laying it flat to then either cut by hand, or if we're going to use a digital fabrication method, then laser cut or CNC, so that we can wrap this object back up into its three-dimensional form. There are some constraints that we'll learn along the way that are related to this process, but I'll talk you through them as we get into it. So I'm going to just go ahead and get started then on building up one of these platonic solids, which is going to be a tetrahedron from scratch. So the first thing I'm going to do when I open up a Rhino file is I'm going to go into either a base layer that I already have. So in this file, you'll see default, which we just have the structure here, the kind of curves laid out for us to have a grid that we can then populate as we move through the steps of this modeling exercise. So I'll be populating those, but we actually have this layer locked currently so that when I select over it, I cannot edit any of those curves. That is very helpful for us so that we don't go in and just move our grid around as we're trying to model. So I have that locked. If I wanted to unlock it and move it, now it's selectable, but I'm going to just go ahead and keep that locked. If we wanted to hide that grid, we just turn the light bulb off, and now we can see our world axis, and we still see our text annotations because those are on a different layer under annotations where we have text and dots. So the dots are going to be cyan colored actual floating text boxes that are going to kind of populate and always face the camera so that we can see them from anywhere in our scene. And those are going to be tags on individual geometry types, which you've seen in the project file from the first video. So it wasn't shown in the video, but it is in that project file if you have access to it. The text layers that we're seeing here are just under text, and those are just text objects. So we can click them. If we don't want to be able to click them, then we can just go ahead and either lock that individual layer, or we can lock the overall annotations layer, because we don't need to be editing any of those right now. And as I mentioned, in those layers, we will see additional information to the left and right that describes some of the steps and operations as I've gone through them in this video. That's going to be populated after I finish up this video. So that's why you don't see it in my video, but you may see it on your project file. So then the last layer that we have, which right now is empty, is geometry types. So these geometry types is just where we're going to be populating each of the steps of this video. What we could say here is just intro to modeling. So we can name that layer by just clicking on it once, or click once to kind of activate it, and then click again separately to enter into that text editing to rename, and then you can type whatever you'd like for that layer name. The check mark is on, meaning that is our current layer, so if we make any geometry, it will apply to that layer. You cannot lock or turn off your current layer, so just keep that in mind. And even if you are activated on a sub layer, so a layer under here, which we'll make in a moment, you cannot turn off or lock a layer that controls or is above that sub layer. So to make a sublayer, we just go up to the top here in the Layers tab and click New Sublayer, and we can just call this Step 1. And maybe we'll give a little bit more information, and what I'll just say is I'll probably just, actually we can call this, instead of calling that Step 1, we can call it Tetrahedron, or Drawing Tetrahedron. So we'll have a layer drawing tetrahedron, and then inside of that we'll make additional sublayers, which we'll call O1, O2. I don't know exactly how many steps we'll separate this out into, but let's just say 4 to start. So drawing tetrahedron, and then we're going to step through each of these steps. So I'll double click into our first one so that we can make that our active current layer. And then I'm going to just zoom in here towards the origin, which is this middle kind of rectangle cell space. So we know that in a tetrahedron, each of the sides or each of the edges are going to be equidistant. It has 4 faces, and it is a kind of triangular pyramid. So if we know those things, we could just type in pyramid. We could change the number of sides to 3, and then this is going to give us a center of inscribed pyramid, so inside of a circle of a given radius. So if we just draw this out, and then draw this out, if we were using exact numbers there, we could control that to be equidistant. So I can hit enter again, click to make the center. I can now type a number, let's say 10. Although keep in mind, this is going to be the radius of the circle that defines that inscribed pyramid. So it's not going to necessarily mean that the edge lengths are 10. So that will be 10. And then click to make that corner. And then the height, I'll say is 10 again. So by modeling the pyramid this way, since we're defining 2 different aspects, one is the height and then one is the radius of the circle in which the pyramid base is inscribed, we're not actually resulting in even equidistant edges. So you can see here we have 14.142 and 17.321. Now all of the base edges should be 17.321, and all of those kind of top edges leading to the point should be 14.142. However, those are not equidistant values. Now we could do a little bit of math to ensure that that is equidistant from the pyramid platonic solid command, but a different way of going about it to really understand the geometry is to just draw it out here using exact values. So we're going to start here by drawing a point in space. Now this doesn't exactly matter where we start this point. We could do it on the origin if we wanted, so that we know exactly where each of these points are drawn. Or we could just, keep in our mind where the starting point is and move or translate additional operations from that base point. So I'm going to just click to deposit a point in space. And we're going to say that we want each of these edges to be 10 units in length. So in this first step, I'm going to take that point and I'm going to copy it with the gumball or use the move command. So type move, hit enter, click on that point in space, type 10, enter. So we've now moved that point, but we've now lost the original. So if we undo that, select the point again, and instead use copy, then this is going to duplicate that point just as a reminder. So now if we select that original point, you can see it's drawing that line out, which is just a representation of the translation. And then we have that endpoint, which is where that point is going to be moved to. If we type in 10, hit enter, it's now giving us an option to click. So it's locked it to 10 units, but we can move it 10 units in any direction. So I'm going to just move it in the x-axis 10 units and left click, and then hit enter to release. So we now have 2 points here, 10 units apart on the x-axis. Okay, so I'm going to now move these up to the next cell, and we'll get started on the second step. So this time I'm going to copy by just hitting Alt and then left clicking on this green arrow, typing 20 because these cells are 20 units wide, and then that will move it into cell 2. I'm then going to right click, so first left click just to make sure that we're selected on that O2 step layer, and then right click on that layer and select change object layer. So this actually changes the structure of the file so that these objects are applied on that layer. It will just help to keep our things organized as we move through this file. Now that we're into step 2, I can double click on step 2 to make that our current layer. And if we wanted to hide the first layer, we could just go ahead and turn that visibility off with the light bulb there. If we know that we're on that step 2, sometimes I like to just select those points and hit zoom, enter, and then we get this second set of commands. We want to zoom selected, so the shortcut is S for selected, and then hit enter. It's going to zoom us in there, focusing on those 2 points in space, which is great. And now we can orbit around just those 2 points. Okay, now with O2 as our current layer, the next step that we're going to want to do is draw 2 spheres centered on each of these points, extending to the other point. The reason why we're going to do this is because actually the intersection of we can think of it as either 2 spheres already, or we could just draw it as 2 circles for now. That intersection between them is going to deposit a third point that is equidistant. So if we go ahead and do this, we can type circle, center point on the first point, and then drag it out to the second, and now center point on the second and drag it out to the first. And if we select both of these and type intersect, enter, it's going to give us 2 points of intersection. So all we need is 1. We'll just use the top one here. And this is going to give us our 3 base points. So just to double check, if I type distance, I can double check that this is 10 millimeters. So the first 2 points are 10 millimeters away from each other. And if we check that second point, that's also 10 millimeters from the first and 10 millimeters from the second, which is exactly what we want. Okay, so once we have that, what I'm going to do is just go ahead and copy all of these up to the next step. they're spilling over, but that's okay. We'll leave it for now. And I'm going to go ahead and change these objects to step 3 and then double click to make that my current layer. Once we've deposited the points, we don't need those circles anymore, so we'll leave those in step 2. I'm going to zoom selected on these 3 points. So now what we're trying to do is to make a 4th point. So we already have 3, that's going to be our base, but a 4th point, which is going to be the top point of this tetrahedron, which we also want to have an equidistant length from each of these 3 points. So like we did with the circle, we can do a similar operation, but with a sphere to get the 3-dimensional intersection. So if I type sphere, center it on the 1st point and go to the 2nd point, and then center on the 3rd point. Oh no, if you're snapping to a grid like I am, I'm going to just turn off grid snap so that we can snap exactly to this point here. So snap there, so our sphere is centered around that 3rd point, and then end this sphere at our 2nd point. So we now have 2 spheres where the intersection between them is going to be a perfect circle. So if I select both of these objects, hit Shift, and left click on both with Shift held to select both, and then type intersect, enter, it's going to give us a perfect circle in space. Okay, so now if I select everything in this step, it's getting a little bit crowded. I'll fix this by maybe scaling them down for your base file. But in this next step, if we wanted to select those last things we just moved, we can type SELL, select last. It selects everything we just moved, and we can go ahead and change that layer to step 4, double click to make that our current layer, and we can delete each of those spheres. So that gives us 1 circle of intersection, but we need now to do a second set. So right now we have a circle that is drawn vertically from, let's call this midpoint, but point 2. So point 2 in the base of our tetrahedron. So what we want to do is find a point on this circle that is exactly the edge length distance, which we know is 10. So 10 units from each one of these points. So what we need is a sphere drawn here from this base point, or this kind of middle point, point 2, which has this vertical circle drawn out, but a sphere drawn from this point now to one of the other points. That is going to ensure that the radius is of unit 10. We know this because the centroid is at point 2. The distance from point 2 to, let's say, point 3 is 10 units. So if we end the sphere at that 3rd point, then we know that the radius is going to be 10. So then wherever that sphere, the surface of that sphere, which we know happens at radius 10, intersects with this vertical circle that we've drawn as the intersection of the 2 previous spheres, we know that's going to be exactly at unit 10 away from each one of these 3 points. So if we go ahead and do that, draw our sphere from this point where the vertical circle radiates from to one of these other 2 points. It doesn't matter which one, because you can see as I go back and forth between them, since the radius is fixed, it's the same, 10 units, it's going to be the same either way. It's a sphere, so it is equidistant on infinitesimally so at all points. So if I go ahead and click on one of these other points, we can see that there is a point of intersection, actually 2 points, one at the top and bottom. We're just going to focus on the top one though. So now if I select both of these objects and then type intersect, we can see here that we've deposited this point. So what I'm going to go ahead and do is select everything inside of there, I'm hitting Control, left clicking on that other sphere which we've grabbed just to deselect it, and you can see inside here that we have our base 3 points, we have that point of intersection, our circle, sphere, and then that other point of intersection. So I'm going to just copy all of this up 20 units. I'm going to make a new layer called 05. I'm going to right click, change object layer, double click to make that our current layer, and then go ahead and delete that sphere. If we want to, we can also just add an additional step, which is taking this, cleaning it up to get only the 4 vertex points that we need or care about for this tetrahedron to be built. So what I'm going to do is highlight over this. I'm going to copy it up again. We're going to make another new layer, 06. I'm going to right click, change object layer, double click to make that our current layer. And I'm going to first delete this bottom point of intersection that we don't need, and then delete that vertical sphere. So now we just have 4 points inside of this cell, can zoom selected, and now we just need to draw each of the faces. So the faces are going to be drawn using a command called surface point, which is going to allow us to deposit the vertex or control points of a given surface to make a plane or folded plane with that. So if I type surface point and then hit enter, this is SRF-PT, which is abbreviations for both of those, and then hit enter, we give an option, or we see an option for adding the first corner of the surface. So we can do our base first. So I'm going to just choose, let's say 0.1, and then 2, and then 3, so third corner of the surface. And then we also have an option for the 4th corner of the surface. So if I just hit enter, we would finish this with 3 vertexes. So if I hit enter there, 3 vertexes, and you can see that there are 2 lines, which are ISO lines drawn on the surface from the midpoint of each of our edge lengths. So we could use that, that's perfectly fine. If we type though, with this surface selected, untrim, and then select one of these edges to untrim, you can see that actually what this is doing is it's drawing a much larger surface and then basically cutting it in half, right? So it's a kind of mirrored version of that surface, cutting it in half or trimming it to give us a trimmed representation. And this is because really what it's looking for is 4 corner points to that planar surface. So if I hit enter to get out of untrim, delete that surface, go back to surface point, hit enter. This time I'm going to deposit 4 points. The 4th point is going to be the same as the original first point. The reason why we do this is we close it out to just tell Rhino, hey, we're making a surface. It has 4 points, but that 4th point is the same one. So it's a totally untrimmed surface, complete. If we go to untrim it, it will not untrim. So we don't run into those issues of it being a kind of messy or extended surface. So if we click here again, click on the 2nd point, 3rd point, and then back to the 1st, you can see now we have ISO curves drawn from the 1st point to the midpoint of the 2nd edge, I guess we can call it, and then we have a line drawn across probably about at 1/3 the area, I believe is probably what that is showing. 1/3 the area there between those 1st edge and 3rd edges. So now if we were to type untrim and then select an edge to untrim, you can see it's not applying that untrim because this is a complete non-trimmed, it already is untrimmed surface. Okay, so if we go ahead and do that for now, each of the other faces, we're just connecting as each set of 3 points. So I'm going to just hit surface point again, and then go from point 1 to point 3, and then to point, or let's go point 1, let's call that point 2, and then 3 is back here, so we'll call this point 4, and then back to point 1. And now again, we'll do point 1, now 4, 3, and then back there. So we can even see that we're starting to align with the specific ordering of those points. We're aligning our ISO curves there. And now here we can do, let's do from here 0.4, and then just go around to close off this geometry. Now all of our ISO curves are totally inline oriented to match each other. Okay, and now the last step here is to select all of our faces, and then we're going to copy it into this last cell, make a new layer 07, change the object layer, double click to make it our current layer, and we just want to join these together. So now we have one completed tetrahedron, and just to prove that each of these edge lengths are equidistant, we have an edge length of 10, 10, 10, 10. And we'll get to why this is significant soon, but the basic idea here is that if we were to orient or translate this in any way, let's say, so we type the command orient. We have an orient, which is just 2 points, or orient 3 point. We want 3 point because we actually want to apply three-dimensional rotation. So we can say orient 3 point. It's going to ask us for a reference point 1. So what we're going to do is just select one face, and we're going to go counterclockwise for the reference points, and then clockwise for the target points. What this does is it basically copies the thing onto itself, but by kind of translating it and flipping it. So reference point 1 is point 1, 2, 3, and then we're going to go just in the reverse order, 3, 2, 1. So we flipped it. Now if we have copy on when we're doing that, which is one of these sub options, so copy, yes, we can do that same thing clockwise, 1, 2, 3, all on the same face, and then 3, 2, 1 on that same face. So we now have these two tetrahedrons starting to assemble, and we could keep doing this. So counterclockwise, 3, 2, 1. Oops. I accidentally went counterclockwise both times there, so let's do that again. So counterclockwise and then clockwise, 3, 2, 1. So we're starting to aggregate or assemble these in space onto each other, and we can do this with any of these faces because we know all of their edges are equidistant. So I could even do it with this middle one now, counterclockwise, and let's do clockwise. I could even do this where if we keep it the same, so let's say counterclockwise here. Now if I go clockwise, we can now place this on any surface as long as I keep doing it clockwise. So I can now just keep clicking, and as long as my orientation is clockwise, we can continue aggregating these tetrahedrons. Now, it doesn't mean that they fit perfectly together and make continuous space-filling geometries, because they don't, or at least a regular tetrahedron does not. Other types can, but the equidistant edge lengths means that they're really great for aggregating and flexible in that we know every single face is able to match or pair with any of the other faces present. An octahedron is similar to these tetrahedrons, but instead of being three-sided, it is four-sided. So still each edge length is equidistant, but it is going to be a base rectangle rather than a base triangle. So if we just go over here to the right side, we can go ahead and start our octahedron. So we didn't need, I guess, that last one, or maybe what we can do is zoom in and we can say that's going to be layer 8, and we can take our assembly, copy it up, change that to layer 8 there, and then just delete these so that we just have our base tetrahedron. Great. Okay, so now we're going to jump into building our octahedron, which is going to be a pretty similar operation. So the first thing we want to do is go to where we have our layer drawing tetrahedron, make a new layer from there so that it's under Intro to Modeling. And we're going to call this layer drawing octahedron. And now we'll just match these same number of steps. So 8, so I'm going to make a sublayer 01, and then we'll do 02, 03, 04, 05, 6, 7, and then finally 08. Now we can double click on that 01 layer, and we'll get started here drawing our octahedron. So very similarly to our tetrahedron steps, instead of starting with 2 points in space, we're going to start with a kind of base for our geometry, draw out intersections using spheres so that we can ensure certain radii, fix the edge lengths to be equidistant, and then we'll get those equidistant edge lengths and draw out our surface faces. So the first thing that we're going to do is type rectangle, and we're going to draw out a rectangle. Again, doesn't matter where the starting point is, so we'll just put it somewhere in this cell. So click to do that first point. But then we want to make sure these edge lengths are 10 and 10. So that's going to be a square subset of a rectangle with all equidistant edges. I'm going to go ahead and just copy this up to the next cell, change the layer, and double click on that second layer. Okay, so again, similar to the tetrahedron, we're going to draw our intersection geometries, but we're going to just start this time with 2 spheres. So we're going to go from the center at, let's call that point 1, and then this is going to be 2.2, and then we're going to do from point 3, also 2.2. So this is going to give us a circle intersection from point 2 to point 4. So we can go ahead and select both these spheres, type intersect, select all of that, copy it up, change the object layer, make that our current layer, and then go ahead and delete those spheres. So right now we have a circle drawn out from point 2 to point 4. The next step that we want to do is draw from our point 2 another sphere, which is going to be our intersecting sphere. Right now it's a little bit out of view, so I'm going to just move this up slightly. There we go. And now draw another sphere from point 2 to any of these, either point 0 or 1, I should say, or point 3. We don't want to do it to point 4, as that would be the diagonal, which is not an equidistant radius of 10 units. So we can do point 3 or point 1. So I'll do point 3. And just like last time, we have now a point intersection, actually 2 points of intersection at the top and bottom. So similarly to previous ones, we're going to select all of our geometry, copy it up, change our layer, double click to be at layer 4, and now we can select the sphere circle and type intersect, and then delete the sphere. We can delete the circle as well if we would like to. So now we have 2 points hovering over each of the, well, dead in the center of this square, but now they can be drawn out from each of the corner points of this square. So the next step is a really kind of straightforward one that's not so necessary, but we just want to translate this rectangle into 4 corner points, which is what it's composed of anyway. So I'm going to just go ahead, copy this up to the next cell, change the layer, double click to make that our current layer, and I'm going to type point and then just draw out corner points at each of these rectangle corner points, and then delete that rectangle. Now I'm going to copy this up to the next layer. Make sure that that's hitting Alt and then copying it. Okay, and now change that layer, double click. So that is our now current layer. And just like last time, we're going to use surface point. And we're not actually going to make the base here that rectangle. Instead, we're going to draw both a top set and a bottom set of faces so that we'll actually end up with 8 total. So 8 referencing the octahedron. So these now are still going to be 3 vertex faces, so triangle faces, but there are going to be a total of 8 of these faces making up the octahedron. So we can just go ahead and we can do it clockwise, counterclockwise, from this top point to this bottom one, so 0.2, 0.3, and then back. Then we can just go ahead and do these all the way around like we did for the last one. And again, I'm drawing out 4 points here, so back to the original one, just to control our surface trimming so that they are non-trimmed surfaces. Okay, and once we've done these for the top, we could just go through and do the same thing for the bottom, or we could type mirror, which is going to allow us to flip or copy and flip, which we'll use this top portion down. So mirror, copy yes, and then we're going to click on 3 point, which is going to allow us to draw 3 points to define a plane for the mirroring. So 3 point. And then we're going to just click 3 points of the base rectangle. So 1, 2, 3. It's now copied all of those surfaces down. I can select all 8 faces. So we've got all 8 selected. And then just copy it into our next cell. Change the layer to 7. And I'm going to go ahead and join. So now we have an octahedron made, which is a closed solid polysurface, just like our tetrahedron. And we can double check that each of these edge lengths are equidistant. So that's 10, 10, 10, and we'll just check the bottom as well. 10, 10, 10. So not only is this an 8-sided equidistant face, or equidistant edge rather, I should say, set of triangular faces, but it's the exact same triangular faces that are present in our octahedron, or rather tetrahedron. So what we can do is now copy this into our last layer. We can go ahead and change this to our 8th layer and make that our current layer, so step 8. And instead of just orienting this octahedron on itself, which we can do similarly with the orient 3 point, go counterclockwise and then clockwise. So that orients on itself perfectly. But we can also take our tetrahedron and orient it onto our octahedron as well. So if I select that tetrahedron and then go counterclockwise and then select on any of these faces clockwise, we can now place that tetrahedron. So now both of these are starting to stack together. And if we actually orient these regular octahedrons and tetrahedrons in a stable configuration, so instead of stacking them like that, we can actually rotate this tetrahedron down. So rotate 3D, start axis, so axis for rotation. I'm going to just use this edge here, clicking on each point of the edge, each endpoint. And then angle, so I actually want this point here, so this end point of the tetrahedron, I want to come down to meet this octahedron point. So I'm going to grab that and then just move it down there. So we now have an octahedron here paired with these two tetrahedrons. And if we think of these as like a group geometry, I can now type copy, and we can make axial arrays by just copying all three of these units, and they perfectly nest into one another. Not only do they perfectly nest into each other to make this kind of linear array, but we can also copy it from here to any of the edges, and we can start to stack them side by side. So these are actually continuous space filling geometries. So for aggregations, these are going to be able to continuously fill whatever space they need to. Obviously, you do have these kind of leftover geometries, so it doesn't mean that it's going to perfectly fill the entire bounds of whatever the bounding volume is, but they can pack evenly or continuously whatever that volume is, minus some given edge constraint. So now to finish off this video, what I'm going to go ahead and do, I'm going to delete a few of these just to clean it up and keep it in its bounding box. So I'm just selecting through and then clicking delete. I'll go ahead and keep one set of this tetrahedron and octahedron combination, and then I'll just delete the rest there. So we'll keep one of those. We can also orient this so that it sits flat instead of on its edge. So we can just select all three, orient 3 points. And as long as our scale is set to no, we can then just select any 3 points on our construction plane, and we can orient it flat, because it will snap to the default axes. So we did have copy on, so I'll just delete that original one, but it's now sitting flat on the ground there. Okay, so I'll just keep this as that final iteration in step 8. And now what we're going to go ahead and do is add a kind of last combination geometry, which is going to just be me stepping through combining using Boolean operations, using Fillet Edge operations, and then going through a couple examples of unrolling and really kind of thinking about what these geometries are producing intuitively from a kind of design standpoint. So what I'm going to do to start this is maybe just start with this base geometry we already have here. I'll copy this up, and then I'll just place it in the middle here. So if we're starting with this geometry, and I know that this is going to be fixed, what I'll just go ahead and do, I'll make a new layer for it, and we'll call this, I'm going to just call it combinatorics. It's not, we're just going to be intuitively modeling here, but it is going to lead to some kind of ways of combinatorial thinking, which will come later on when we start getting into aggregation types and logics of aggregation or stacking and assembling. So I'm going to call it this for now. It's really just a kind of combined set of aggregations that we're manually and intuitively arraying. We may even kind of break the logics or bounds of these tetrahedrons at some point to start to kind of produce difference in geometry. So I'll say combinatorics, and we're going to select these objects, change their layer, and then we won't have sublayers for this. I'm just going to double click here, and we'll just have the final geometry shown in coordination with the video as I walk through it. So if I know I want these to be my base geometries, and we have our base octahedron and tetrahedron to the left here, then what I'm going to do is just combine these from the start. So I'm going to type Boolean union. It's now union these as one geometry, so when I click, it selects all of them. And since we have certain faces that are already aligned, what we can go ahead and do is clean it up with merge all coplanar faces. So when we type that, it actually takes each of those faces that were aligned and makes one complete untrimmed face. So at least in this case, untrimmed. Untrimmed face that combines what were coplanar faces. So that's a good way to prevent the kind of messiness that often comes with repeated Boolean operations. So we also have the kind of base to this geometry, so it's laying flat. So I might kind of aggregate on this a little bit with two of these geometries to try and get some kind of cantilever conditions, maybe some pocketing, things like that. Maybe try and build up more mass to kind of produce asymmetry in the composition within what is a kind of stable logic of aggregation. So let's start here by, I guess we can do tetrahedron, and I'll do orient 3-point, start counterclockwise, and then we'll do clockwise to start building this up. Okay, we're gonna need to start building it taller. So I'm gonna look here and again, clockwise, try to start just kind of through clockwise orienting, copy these up to get some height first. And then once we have that kind of base shape and height, then we'll start filling it out with kind of geometric mass. Okay, so I'm hitting escape to just end that orient command. So we're getting a little bit off balance. Maybe we need a little bit of mass here to kind of build it out or thicken it. I'm going to take the octahedron and start building that up and see if we can kind of fill space continuously with combinations of octa and tetrahedron together. So we'll see what we can do there. We'll at least have one extension here and another extension here, and that should be enough. Maybe even another foot that touches down if we can get that going. So I'm going to select this octahedron, orient 3-point, counterclockwise on one face, and now we're going to use this face clockwise and this face clockwise. Oh, it looks like we've gotten the wrong point selected there, so that happens. I'm going to just undo with Control-Z, and let's just make sure that we're zooming in and actually getting the right points when we go to orient. So top point, that second point, third point, okay? And now when we come back over here, we want these clockwise, 2, 3. That looks better. 1, 2, 3. There we go. Okay, so we're starting to build up mass. It looks like we can fit a, let's see, that would be, I guess we might not be able to fit an octahedron there. I think it's asymmetrical. It looks like it would be asymmetrical, which makes sense. You shouldn't be able to fit 3 octahedrons evenly together to fill space, but we can go ahead and give it a try. Now clockwise, and yeah, you can see that that is not going to work to stack, but we can try one of these tetrahedrons, so counterclockwise. It's not going to pack evenly, and it actually does make a collision there and does not intersect. So we'll just keep those, and then we'll kind of build mass up off of those slightly. Maybe we'll have an additional piece right here, so I'll use this octahedron and then just do a counterclockwise and then clockwise orientation so that we can build that mass up there as well. Okay. And now what we can do is on each of these octahedrons, we can actually build up that kind of stable unit. So copying counterclockwise and then clockwise, and we just need to find 2 open faces. So here we have 2 open faces on either side. We could also choose to do, they have to be counter to one another. So I guess we could do these as well, but it's going to intersect there. We could do this one here, so maybe we'll do that. So we'll do one here, and then one here. So now we have that stable geometry coming off of that. And then let's try one here as well. Hopefully that doesn't intersect, and it does not. And then we can do one off of this face as well. That does intersect, so we'll just go back through that and delete that. Okay, I'm going to just delete this one that intersected. So when we're looking at this, really, we should be looking for maybe more stability. We're losing a lot of mass here in the middle, but this is going to be a good example as a kind of base for generating some like asymmetrical conditions, somewhat related to the kind of aggregation logics of this. If we wanted to do one quick, additional step, we could maybe copy this set of stable 3 and then just start to fill in a little bit more space here. So copy this one as well. So we get these kind of extension geometries that start to branch out. One thing I'm going to look for, though, when we go into editing this is to kind of fill in this middle space. And maybe that's where a unique kind of difference in geometry can appear from some other type of primitive or way of constructing geometry. It doesn't necessarily have to be always primitives. So what I'm going to go ahead and do now is Boolean all of these together by typing Boolean union. We're going to wait for that to process. If it doesn't tell us Boolean failed, then we're good to go. That means that it is completed and it's Boolean union, all of these elements together. We can then type merge all coplanar faces, and it's going to combine any coplanar faces. So it's a little bit messy here. We can see some edges that are not aligned, not following the aggregation logics, and it gets a little bit thin and unstable in the middle. So that's something that we're going to want to go in and adjust as we kind of continue editing this geometry. One other thing to consider is when you're performing that Boolean operation, if you get a failed operation, just go ahead and Boolean individual elements in steps. So you kind of sequence through it, adding one to another. Just take it one by one, that's totally fine. Sometimes it has a difficult time where edges are perfectly aligned on one edge. It doesn't really know whether or not those do overlap or not because they align so perfectly. So just go ahead and go one by one, and whenever it fails, just do a different set of 2. It's totally fine. Eventually you should be able to get all of them Boolean together. And as you do get successful Booleans, remember to just merge all coplanar faces. So we now have that all merged together. So what I'm going to try and do here just to start is start getting some smooth geometries into this base geometry. Now, since we have a goal of this being a digitally fabricated element or something that we could potentially unfold in order to build as a model, right now we could do this by just selecting this object, and we actually know the way that we constructed these, every single face is a planar face, meaning it can be made out of an entirely flat sheet. This is incredibly useful in the construction industry or building industry of any type, even product design, because it means any manufacturing method, centering around sheet goods can be used to fabricate this. So we can do this unwrapping procedure by typing Unroll Surface, and this is going to work with any singly curved or planar geometry, meaning it doesn't have 2 axes of curvature. So we'll talk about this in a bit, but this is going to essentially rule out most of our swept geometries if we have 2 axes of curvature there. So our profile or sweep sections and sweep rail both have curvature, then that's not going to be eligible for this type of operation. But things like extrusions, most lofts, unless you use particular loft types and multiple sections, then we won't be able to do that, but that's something that we can get into. It's within options and lofts. The standard loft options with regular ruled surface sections are going to be unrollable, but this is the kind of nuances of some of these commands. But we also have a kind of base idea of certain geometric types. where they are guaranteed to be singly curved, meaning they can be unrolled using these unrolled operations. The reason why unroll surface does not apply to doubly curved surface geometries is because they actually require distortion to unwrap. Think of any sheet of paper. If you try and bend that sheet of paper on two axes, it's going to wrinkle. It doesn't do a good job. It can do one axis incredibly easily, but it's not going to be able to bend in two axes without wrinkling or some deformation. And that's the same as this unroll surface. So it's going to basically easily unroll geometry that is singly curved or planar, but it's not going to be able to deform to unwrap any doubly curved surfaces. There are other operations that can do that, but they do have deformation, which means there is a change in the geometry, so it's not the exact undistorted version. So that's going to matter a lot when we get into fabrication methods and thinking about these types of things. Okay, so it's asking us right now to select curves, text dots, and points on the polysurface to unroll. So we're going to just unroll this particular polysurface geometry. We don't need to unroll the curves. So we already have it selected. That's totally fine. We're going to say explode yes for now. Later on, we will change these options. But for now, we're going to say explode yes. Labels no. So labels would just give us which face in 3D matches with which unwrapped face. So if we just leave that at no for now, and then keep properties, we can say yes, it will just keep it on the same layer with the same materials. And later on, we'll get into even preserving the digital texture that we've applied. So if I hit enter, it's going to unwrap each of these geometries exploded and arrayed or laid out from the origin all along the x-axis. So it finished. And now if we click off, we can see each one of those faces arrayed all the way. We can see that they're not all the exact same, but a lot of them are the same. That's because our base surface is the exact same equidistant edge length, meaning in the tetrahedron and octahedron, we actually have all the same faces. So we even have a unified panelization measure or method. So this means we could have built that geometry with entirely unified panels. So only one panel to make that entire complex geometry. But because we use the merge surface operation or merge all coplanar faces, we do have some that are going to be different. This is totally fine. Depending on the constraints of the project, we may want unified faces, but this is going to actually make assembly a lot easier if we have these larger faces that are able to be made still in a sheet material. And we know all of these are planar, so it's not an issue to cut that profile versus any of these profiles. If it was more complex three-dimensional geometry we were fabricating, consistency then is key, and getting a kind of repetition out of molds is also going to be key. So if we undo this operation, go back to our geometry, and then type unroll surface again, and this time hit explode no, enter, what this operation is going to try and do is preserve the connections between all of the faces on that geometry as it unrolls it. And you can see that this makes a really incredibly complicated geometry with a bunch of overlaps. So if we explode this now, we're going to see that actually there's several overlapping faces here. So it's not quite exactly what we need. We would want to move this face out so that we can still fabricate it. We'd have to move this face out, and it starts to get really messy and complex with all of those overlaps. A different way of going about it is from the very start, we can go into this geometry, we can use extract surface, and we can extract a number of surfaces. So let's say we can just do these to start. So extract those surfaces, join them back together, and then unroll surface, explode no. So now with such a limited number of surfaces, if we just pull this out here, we can see that actually there's no overlap, but they're still all joined relative to their three-dimensional edge joining pattern or organization, which means we can easily still fold it back up. If we were to laser cut this, we would just want these inner edges to be scored or dashed so that we can fold it either inward as a valley or outward as a mountain. And then this overall outline would just be cut through the material so that we actually get this as one continuous piece. So that's just to get us thinking a little bit about these objects as unrollable geometry that we want to think about through digital fabrication. So if I go ahead and select all of these, join them back together, we now have one closed solid polysurface again. So before we get to that step of unrolling, I'm going to introduce a couple more singly curved geometric types, the primary one being a cone. So I'm going to type cone, enter, and I'm going to draw out here the base of the cone, and then I'm going to draw out the height of the cone. And what we're going to do with this geometry is use it first to maybe infill a couple of these kind of mid sections, and then eventually we're going to use it as a bounding geometry to kind of contain or reshape the bounds, aligning some of these surfaces that right now are misaligned and looking a little bit messy. So the first thing we're going to do is scale this down, and we're going to try and align this from the base, kind of build up more mass in this midsection. What I'm trying to do is get it in places where we're missing mass, so more like in here. Then we can copy this up. Now we're starting to kind of lose a bit too much of that kind of tetrahedral like character, the kind of sharpness of that geometry. So what I might do instead is just leave that at the base, or actually just go ahead and scale this up from the very start, and we'll build up that mass in a different way. So I'm going to just scale this up, move it up so that we just have a few of these edges intersecting. I'm going to change the orientation on 2 axes, and the hope here is that we're really using the round part of the cone to do the kind of shaping of this geometry. So we're hoping to use that conic surface to kind of reshape and make a little bit cleaner the geometry that we just aggregated previously. So with it in that position, I'm going to select both solid geometries and type Boolean intersection, enter, delete input, yes, enter, and now we have the output of that Boolean intersection. So you can see we're still missing quite a bit of mass. We've now totally severed certain portions. So I don't think that particular placement is going to work very well. What we might actually want to do even before the cone, so I'm going to just hide this cone, and we can re-show that and then use it in a moment. But I'm going to start by actually taking this tetrahedral aggregation and building up more mass on a different axis, though, by just rotating this. It is getting quite a bit messy here. We'll see if we can clean it up a bit. Try just orienting, not copying, to get some of these edges aligned a little bit better. It's at least building a little bit more mass, and then we can Boolean union those together, merge all coplanar faces. Okay, we have some things starting to come together. And before we get into the cone, I'm actually going to draw out a bounding box around these volumes, shrink it a little bit so that we first start with a bounding box alignment. So with it selected, type bounding box. This is going to draw out a box around the entire geometry with everything contained. Select that box, hit Shift and then click on one of these small boxes on the gumball. That's going to allow us to scale. We can scale it in slightly to just trim off some of the outlying geometry. Select both the box and the geometry itself, and then we're going to Boolean intersect these two geometries. So this gets more edge alignment on the outer perimeter, just looking a little bit cleaner, although we still have some messy bits on the inside. And now I'm going to show selected, select that cone, and let's see if we can just shave some parts of this off to get a little bit more kind of interest here with some curved profiles running through this tetrahedral aggregation. So select both, Boolean intersection. It's going to take that kind of Venn diagram of them. It's a little bit too curved, too much of that curved surface showing up on the edge there. So I'm going to just move this away so that we don't have quite as much, and then maybe up. So we just want some clippings just for a little bit of that character to show up. Boolean intersect. I think we probably want a little bit more off the back corner here versus this one piece that we keep carving into. It seems like it's kind of off balance when we use that, so maybe I'll flip this around, just using the gumball to rotate this object in space. It's a little bit quicker and easier than using the rotation tool always. Now we have the bottom plane of our cone that is shaving off this bottom corner. We probably don't want that actually, just because it's going to carve a flat plane through that corner. So we want to pull this back, and we can rotate the cone as necessary to only shave off certain portions. So I'm going to try and rotate this cone and move it down so that we're not using that base to carve into the object. Okay, let's try this. Boolean intersection, enter. Still a bit messy, but we're kind of, now getting this one sweeping surface moving through here with some of the patterns of the tetrahedral aggregation, and then some clippings from that bounding box on it as well. So we know that a cone is a singly curved geometry, and that's why I'm sticking with just using the cone or the bounding box, because we would still be able to unroll this surface geometry, or this polysurface geometry. Okay, so now we have this. It's a bit messy from the Boolean operations. So what I'm going to do is go through a series of different kind of fine-tuned geometry cleanups. So the first thing I'm going to do is try and develop still more continuity between some of these edges, so we get more like coherence or kind of movement or momentum present in this piece. The other thing that I'm going to do is I'm going to go in and untrim, or rather trim, and rebuild certain surfaces that seem unnecessary or messy. Now, I'm going to show a demonstration of this. It may be obvious to you already, but as we think about making these out of paper, a surface like this that's a large continuous wrapped surface, it's going to be a lot easier to make than all of these little tiny crevices, which may not actually add much to the character of this piece. So does this misalignment here add to the character of this piece, or should we just redraw that and rebuild it to be aligned? Same thing with this small little crevice here. Do we want that, or do we want to just kind of clean it up so that we don't have as many of those messy bits to worry about? So I'm going to try and go through and find a couple of those, and we're going to rebuild them so that we don't have to worry about quite as many of those small pieces. And this is a good step to go through with any Boolean operation, because they tend to make quite messy geometries. And generally when we're designing or developing something inside of Rhino, we have quite precise measurements or curves that we're working with. So this is going to be a way of kind of thinking about that curve precision and surface rebuilding by showing you a couple of ways to rebuild a messy polysurface using those. So the first thing I'm going to do is go in and fillet certain surfaces using the Fillet Edge command. And I'll go into surfaces like this, where, maybe to kind of balance this sweeping surface that we have on the left, upper left, on the exterior, we can add a kind of sweeping surface that pulls that momentum in and then kind of around or wraps it into the core of this object. So we can click on an edge, hit enter. It shows us a preview of that radius. If we just hit enter, then it'll apply that radius, do its best to close that geometry. It doesn't always do a great job, which it has not closed, unfortunately. So this is another opportunity which we can actually go in and just rebuild this geometry in a way that makes sense for especially our fabrication technique. We can also type Fillet Edge again and change the radius by clicking next radius. By default, it's 1. We can change this to 0.2, enter, and then we can select the edge and hit enter, and it's now going to apply a radius of 0.2. You can see it's still not closing that corner, probably because there's a lot of junctions happening there, so it's having a bit of a tough time. Now, if we made this too big, like use the radius 2, we would get this kind of extended thing, basically Rhino telling us that it can't do that trimming operation, so it's telling us to do it on our own, and it's giving us this radius to be able to do that on our own. So maybe just to start with, I'll look for certain ones that I do think are going to successfully fillet. So I think this one should successfully fillet and keep the geometry closed, and it does. So I'm going to go ahead up. Looks like it did not successfully close. Sometimes those kind of sneak by, so it looks like maybe there's some crack or kind of opening here where that piece is not able to close. These tetrahedral geometries are tricky, so you do have to be careful as you're kind of working with them that they are closing and that your poly surface is staying as a closed solid poly surface. So that fillet works, and we're getting just that nice scoop there. I might actually make that radius slightly bigger. Okay, so that is too big. So we now have to kind of go back and forth with it to see what actually works here. Okay, so that, to me, that seems pretty good, where we're getting this scoop now, kind of down this side, combining those two elements, and we're starting to kind of pull these things, or some of the momentum of some of these surfaces, towards one another. We can also do a variable radius fillet, just with the Fillet Edge command again, but what we want to do is click, hit enter. When it shows us this preview, we can click on the end of either of these fillet radii. So first I'll click here. I'll actually leave that one at 1. I think that was a good size, but this top one could probably be much larger, let's say even 4. So I'm going to just click, type the number 4, hit enter, and now we have a variable conic radius from 1 to 4. So if I hit enter here, we now can see that variable radius applying to that edge. So I'll just do this to a couple more, just to get a little bit more of that kind of momentum pulled across this geometry. Maybe we'll try a variable one here, where actually we go down to, I think 0.2 didn't even work, so we can try 0, and then we can try a much larger radius here of 4. That does not work. Let's try 2 and then 0. Okay, so that is working to kind of just pull that up, and it did open up our poly surface. So just prior to that, we had still a closed poly surface, and I think it's because these edges here are getting a little bit tight and kind of messy. Let me try adding a fillet just there. Let's see. Okay, so that does stay, so maybe we can actually get a larger fillet in here, which kind of appears as a bracing. Okay, it looks like that's actually closed for us as well, which is great. It says that it's a closed solid polysurface, but you do want to double check those intersections. And then here, maybe what we'll do is try a 0 radius and then a radius of 4 the base. It's going to need to be less than this edge length, so we can try that again with 2 should be less, and then this can be 0. Okay, there we go. So it's still closed solid polysurface, and we're getting a little bit more of those nice radii in. And last one I'll do just that one. It is opening it up, so it's having a tough time here on this edge, figuring that out. So let me see if I can just change that to 0 there. Nope. So it's still having a tough time because this double bend on that end. So what I'm going to actually do is apply the radius, and I'll show you how to clean this up. So I'll apply that. We can see that this is kind of spilling over the edge there. So the way that we're going to clean this up is by first extracting that radius that we just filleted off. So now it's its own surface. So it's definitely an open poly surface now. And we actually want to also extract some of these neighboring surfaces, and we're going to split them into each other and basically kind of construct these splitting planes to work with this radius to kind of build up something that we can then kind of close out this geometry but still keep this radius with. So the first thing here we can do is untrim and select the edge we want to untrim, which is this far edge, so we don't have that kind of weird geometry on the edge of that radius there. And then we can extract some of these neighboring surfaces like this. Now what I typically do is I'll copy this using copy and then in place, and then I'll extend by scaling in the plane. So I'm just scaling that plane up there so that it's still in line, so that we can actually trim that particular radius, with a geometry there that is going to be able to kind of wrap it back into the rest of the poly surface. So I have to take a look here. We actually think we want this surface to continue on the underside. So yeah, we should be able to This is a fairly complex one where we, I believe, just need a joining between this plane here and then this plane next to it underneath. So it's going to be some edge here underneath this radius. So what we want to do is extract this other plane as well. Or even if we don't want to extract that, we can just draw out another plane, 3-point. Draw this on any 3 points of that surface plane and scale up holding shift. And now if we take both of those planes and type intersect, we get the line of intersection between each of those. and that should perfectly align with that radius there. So what we're going to want to do is we're going to want to split this plane with the polysurface geometry and the radius and that intersection line. So if we hit enter there, we can then select, or if we we can either undo and delete. There's several ways to delete, so we'll just do it this way. But now we can just, after splitting, select one of these surfaces. So the one that we want to delete, you can click delete. And I think somewhere in here we have an additional set right there. And we also have some hidden in the geometry in there. And this is why I think it's actually better if we just go ahead and perform the splitting operation here. So use the polysurface, use the line, intersection, and the radius, hit enter, and then what we can do is actually just deselect the part that we want to keep. So control left click, that's the part we want to keep, and now delete everything else that is still in our selection. And then we can delete this original surface, and now we have this new surface that is actually tucked underneath that radius and in the previous plane that we had already had from the polysurface geometry. Now with this plane, we're also going to perform a split, and this split is going to be with this intersection and the polysurface and our previous plane, as well as the radius if we need it. And we can hit enter, and then control left click and left click to preserve those. And now we can hit delete. Okay, so we now get this extra little corner piece here, which was split from that operation, which we can now join with the plane that we just made. That just tucks right up underneath the radius. We can then split the radius with those two planes. Let's do it with the polysurface and those two. So for whatever reason, it's not wanting to split. Let's test the intersection. So it looks like it's almost exactly intersecting. Oh, that would be the issue, is that additional little line which was drawn through, so it just wasn't connecting all the way through. So we now have 3 parts, which we can just go ahead and delete. That radius is now evenly meeting that plane, or the kind of folded plane that we just made. We can select both of these, join them together, select our previous polysurface, join it together. We now have this small triangle that we've added that should be in plane with our previous plane. If we type merge all coplanar faces, it should just go ahead and fix that for us, and then we can delete these construction curves that we were using. And we now have a closed solid polysurface with that radius, and we also have nice clean edges preserved. So if you ever get into trouble with the Fillet Edge tool, that's the same kind of operation that you need to go through. First, analyzing what the issue is, and then going step by step through and extracting faces or surfaces, drawing out new planes, splitting, getting intersections between them, and then trimming the radius and trimming the planes so that you can create one new clean intersection. If you wanted to now, after you've kind of made those adjustments, you can also go in and try to fillet the edge to even make that transition a little bit smoother. You can go ahead and try and see what it gives us. So it is having an issue with that. You can try a slightly lower radius. It still seems to be having quite a tough time with that area. I think there's just too many junctures. Let's try maybe that. So it can do this other edge. So if we wanted to, we could maybe try adding a radius there, so it kind of wraps in. It's starting to get a little bit too complex there, but there's some nice geometry and kind of flow between some of those surfaces. And this is just, an example piece, so it's not the absolute best thing in the world, but I think it gets a couple points across that I was hoping to make in this video. So now we're going to look at cleaning up some of these Boolean pieces, which is going to look very similar to the cleanup of the fillet edge that we just kind of went through. So the first thing we're going to look for is any portions that have particularly small faces, like that, and we're going to see if we can just go ahead and extract those, starting by making a hole. So I've made a hole there, and now I want to extract the nearby faces. And then we're going to untrim each one of these. So select first that surface, and then that, and then the curved surface, and now we're going to see if we can trim each one of these. So the cone is probably going to be the hardest one. What we want to do with the cone is split with the original polysurface geometry and at least one of these planes. And then deselect that middle section we want to keep. And then we'll still use the rest as a splitting or cutting geometry for the other two planes. So what I'm going to do here is now I'll split this. I think we'll have to do the cone. I'll split this one with the cone as well. And we'll just delete these extra bits and then delete the cone as well. So you can already see we have actually these surfaces starting to now kind of abut, so they meet at that clean edge, and so you can see here as we're doing this, we're actually leaving an open space there. So if I go back to before we have the cone, we have a nice clean piece of geometry there. So I'm going to try and do this by actually just extending this one surface, because all we need is the extension of these top two. So let's try that one. Do need the cone there to get that intersection, but what I'm going to do is copy this so that we have a copy of that full piece, untrim the edge of that cone, split this plane with the cone. I'll just delete that cone for now. Now I'm going to split this surface with our entire poly surface. So now we have that piece extended slightly. So it looks like it can get a little bit further extended there to meet, but I think we're going to have this plane cutting through at that intersection point anyway, and then we'll have the cone kind of finish it out. So this should be good enough as a starting point. So now if we go into untrim that plane, so now we just need to split this with our untrimmed cone, which again I'm going to copy just so that we can still have this piece as needed until the very end. So untrim one of those cones, split the plane with the cone, delete the cone, and then I'm going to take this plane split with our poly surface. And then here we need to kind of fill in this gap. So we then need to, again, just split this surface by this kind of edge at the base here. And then we have our leftover geometry here, which we can go ahead and just split already, delete the excess. You can take this surface and split cone. It looks like it doesn't want to split, may not exactly cut through. So we can come back to that, and it looks like it might be having an issue there as well. So let me try again to split it with the poly surface. It's saying again that it's failed. Okay, now we've gotten it. So now I can go ahead and delete this extra bit. So we just have the portion of that poly surface that we need. We can split this bottom plane, deselect the portion that we need. So we're slowly building this out to kind of remove that messy bit there. And now this kind of outer edge, we just need to untrim to infill that. So if I go ahead and say untrim, now we should be able to take this cone and split each of these bordering surfaces and poly surface to just get this central profile, which we do get, and then we can delete it. And now we have a nice clean geometry there at the edge with none of those little pockets at this corner. And now each one of these should be able to neatly rejoin and join with the original poly surface, which is now nice and closed. And just to be safe, we can merge all coplanar faces to get a nice clean version of this poly surface. So we could go ahead and go through every single little corner, just removing anything that we deem excessive, or we could also go in and just manually model certain things. Like if we wanted this bottom kind of edge to just be extruded straight down and infill, then we can go ahead and extract. So if we extract this bottom surface, I'm going to say extract copy, yes. So we can just copy that and then extrude this surface down. So I'm using the extrude surface command, and I'm going to extrude it down to be even with all of the other flat planes. Now, if we don't want it to look so bulky like that, we may want it to actually be continuous with the previous edges. Then what we could do is, instead of extruding like that, we could extrude a series of edge curves, and we can extrude them at a specific direction using the direction. So this is extrude curve, click direction, and I'm going to just look at the plane above and use 2 points on that edge. So we can draw that out. And I'm going to do the same thing for each of these. So any 2 points on the edges. So those are all now continuous, which is great. And then we'll just do at least one more here. And I'll just make it even with this one next to it. So that's going to give us 1, 2, 3, 4. So that's 4 unclosed faces that we can join together. And now if we just loft 2 of these ends, we can join all of these together, and that gives us a kind of wrapped geometry. We can type cap to produce a cap on the top, which we can then join back into our original geometry. We can then make a plane to cut the bottom off here, and I'm going to do a plane that is from a point on the bottom. I'm going to scale this plane up, select that geometry, split, use the plane to cut, delete the plane, delete the cutting geometry, select our skewed box here, type cap, select both our original poly surface and our new cap geometry. You can see in the properties it says two close solid poly surfaces. I'm now going to Boolean union these together and then use merge all coplanar faces to make it nice, neat, and clean. So now it looks like we never even had an issue there, and it's totally joined with a nice base attached. So we could do the same thing for the middle here if we didn't really care about having this giant hole in the middle, or we didn't want to deal with the kind of pain of going in and modeling that. Or if we wanted to, we could just model a box that happens to be the same size and shape as that kind of inner portion. We can align this box by moving it in here and then rotating it to align with certain elements, like this kind of one piece on that edge. We could move it in slightly so that we don't actually see it poking out quite as much. And I don't mind it sticking out here, but if we wanted to, what we could do is scale this as well. And we want to be careful to scale on the axis since we've already done that alignment. So there you go, we can scale it on the axis there. And it's nice and even with that other piece. And if we wanted to actually scale it vertically, just so that we have it coming up maybe halfway to connect some of these elements a little bit more, we could do that as well. Or we could scale it all the way to really kind of seal up and make solid this inner geometry. So I'll just go ahead and Boolean union these, merge them all, and now we have a lot more of those flush, flat faces. So it does look like we caused a bit of an issue there by merging those faces. So maybe what we'll do is scale that box down slightly. And maybe we can keep it at this level. Okay. So that should have taken the complexity down quite a bit, although there's still a lot more, like in these crevices, that we would be able to go in and clean up if we wanted to spend the time. But for the sake of this video, I'm going to just leave that here, and what I'm going to do is actually do one more edge fillet, which is just on this piece right here. It's not wanting to. Okay, then I will go ahead and skip that. Okay, there you go. It's still a closed solid poly surface. Okay, so now what I'm going to go ahead and do is select that geometry, and I'm going to type Unroll Surface, enter, explode. We can just say explode yes, labels yes, keep properties yes. And I'll move the output of this up to the combinatorics layer so that we can kind of see that relative to our unrolled geometry. Now, some of those edge fillets, if they're happening on curved surfaces, which I don't believe we had any that were, it would give us an error saying that it had an issue making that, but we shouldn't have any as of now, because we are using singly curved geometries. So I'm going to just move this up here to the top, and I'm going to just center it on our cells. And I will move this to a sublayer for Unroll Surface. Change object layer. And then I'm going to make another sublayer, which is called labels. So those labels are just going to be all of these dots, which just tell us which surfaces or which edges align with which edges on the unrolled geometry. So it's helpful for you to be able to visualize to rebuild these things. Now we can actually just go ahead and turn those off for a moment. So you can see the complexity already in 3D, but if we turn on our unrolled surface, you can see how quickly it becomes complex and difficult to deal with. So cleaning up and keeping clean geometry in these early modeling processes is going to be critical. So you might want to spend just as much time in cleaning up geometry as you may in actually like designing or kind of aggregating or constructing the geometry itself. So cleaning up will help you so you don't have quite as many surfaces unrolled. But the other thing that you can do, which I'll just show here, hopefully fairly quickly, which I mentioned as well before, but you can go ahead and explode all of these surfaces, and then you can go back into the exploded geometries and start combining certain elements that you think can unwrap without distortion or without overlap. So if we pick larger chunks and then join these together, we can have individual elements that we can unroll and now say exploded no. We can use labels on or not, it doesn't matter either way. I'm going to just do this one example piece, bring this up here, and add it to the unroll surface. So even for this, we do have one piece that actually did need, it did require an overlap. So if you get something like that, it doesn't mean that all hope is lost and we can't use this one particular group. What you can end up doing is just selecting this, exploding it, selecting that one surface that's overlapped, use the rotate command, and just rotate this to hinge off so that there's no overlap. So we now know that that curved piece is going to fit just inside of that curved edge when we fold it back together. And now we can even go in and just join these all back together. And that one piece is now its own element. And we still have them grouped relatively similarly, but this is going to be a lot easier when we go in and laser cut this and then fold it back up together. So you might have maybe 10 to 20 individual pieces to cut instead of the hundreds that are laid out here. So I highly recommend this second way of going about this. I'm going to just go ahead and copy this over, join them all back together, merge all co-primary faces, and now we should have still it's now giving us an open poly surface. Okay, closed solid poly surface. Great. And okay, then we just have our unrolled surface geometry. So that's all for this first exercise in Rhino modeling. So 3D modeling and thinking through strategies for cleaning up or geometry editing, as well as from start to finish, construction strategies for things like tetrahedrons or octahedrons, which are great aggregators, which we'll look into when we get into recursive aggregation and Python scripting in future classes. In the next video, we're going to be getting into Grasshopper, which is a node-based visual scripting editor inside of the Rhino interface.